All right, folks, we'll get started in just a minute or two. Bear with me. So let me just go to the calendar for a second. So here's our calendar. And it says here, today is April 10th. So we're going to get started in section 10.3. We'll finish that on Monday. And then once we do that, we only have section 10.4 and 10.8 left. So we're not covering all the sections in chapter 10, only these selected sections. All right, so before I get into section, by the way, then folks, this Sunday, there's homeworks 10.1 and 10.2 due in WebAssign. Remember, these homeworks are kept open until May 1st, but try to keep up and complete the homeworks as best you can according to this calendar so that you don't fall too far behind. All right, folks, before we get into section 10.3, I wanted to go back and just do maybe one more example in section 10.2 dealing with law of cosines. All right, and please, if you have any questions or examples from section 10.2, please bring those up.
Hello.
Hi, Gennaro. All right, folks, I'm going back to section 10.2, and just a quick reminder. Here, I'm going to slide 4. These were the formulas we were using for law of cosines. So remember, law of cosines is when you cannot apply the formulas for right triangles. So in section 10.1 and 10.2, we're working with triangles that are not right triangles. So remember, we have law of sines at our disposal. And if law of sines doesn't work, you can use law of cosines. All right. So these formulas here were when you were trying to find the missing side of the triangle. And these formulas on the bottom were when you were trying to find a missing angle. So let me go, I think it was problem number 8 in WebAssign that was a bit challenging. So let me go to that problem. Here it is, problem number 8. So let's take a look at this one. All right, so they want us to find the length of side X in this problem. Now it looks like they already labeled the triangle for us, so that's good. All right, so I'm just gonna double check that this triangle is labeled as sides A, B, and C, angles A, B, and C. And then I'm gonna label the sides as lowercase letters. Now, instead of calling this X, I'm gonna call this side A, just to make it a little easier to match up to our formulas. So the unknown quantity here is side A. Okay, of course they called it side X, but we can call it side A if we want.
The question I had on website was just like that, but I figured it out.
Okay, good. Yeah, let's walk through this, Janar, because this one's a little tricky because it turns out here you can't apply one of these formulas directly yet. All right, well, I'm noticing that they gave me the length of side C, that was 15. They also gave me the length of side B, that was 12. All right, so I know side B and C, and I want to find side A, but they gave me angle C. So notice angle C here is given as 42 degrees. But side A is the unknown quantity. So I might try to use this first formula here that's circled in red. But what is the problem? Why can't I use this first formula? Let me label these formulas as, let's say, formula 1, 2, and 3. Why can't I use formula 1 here? What's preventing me from using Formula 1? Well, I do know quantity B, that's good. I know quantity C, that's good. But to use Formula 1, I would need to know angle A. But notice I don't know angle A yet. So I can't use Formula 1 yet. And you might say, well, all right, we know angle C. Remember, in this example, angle C is given as 42 degrees. Why don't we use Formula 3 then? Because Formula 3 involves angle C. But why can't I use Formula 3? What's wrong with that formula?
We hold on. We know cosine gamma is 42 to cosine gamma.
Yep, and the reason I can't use Formula 3 is for Formula 3, I would have to figure out side A. But if I did that, I would end up with a messy quadratic equation. So Formula 3 is not really well suited to what we want to do. We really want to use Formula 1 here. Because remember, side A is the unknown quantity, right? So if I could use Formula 1, it would solve for side A. So I want to use Formula 1. The only missing ingredient is angle A. So how can I find angle A in this triangle? Is there a method that I could use to somehow figure out angle A? Or alternatively, if I could figure out angle B, that would be good also. Because if I figured out angle B, and then I could automatically figure out angle A, because if I know two angles of a triangle, it's always easy to figure out the third angle, because I know the angles have to add up to 180 degrees. So I want to be able to figure out either angle B or angle A. Does anyone have a suggestion on how I could figure out either angle A or angle B given this triangle?
Okay, if you have a brief description, I know.
Well, how about if I try law of sines and see if that leads me anywhere?
Okay.
Because here's what I'm given. Let me write down what I'm given. I'm given angle C, so I know sine C. I'm also given side B, and I'm also given side C.
Okay.
Would that lead me to be able to find angle B using law of sines? Well, the answer is yes, because you remember I can write this equation using law of sines. So I'm going to write this as sine B over B equals sine C over C. Remember, this is law of sines. Let me circle what I know. Well, I know angle A, I know angle C. I know side B, and I know side C. So this formula is going to let me find angle B, right? Because angle B is the only unknown quantity. But if I know angle B, does it make sense I could then find angle A? Because if I could figure out angle B, then angle A would be the only unknown quantity. So really there's 3 steps to this problem if you want to think about it. Step 1 is find angle B using law of sines. Find angle B. Actually, I'm going to write this. My handwriting is so bad that it's going to be better if I just type it. So let me type it here. So step 1 is find angle B.
Okay.
But if I know angle B,
description,
I'll find angle A as step 2. Using the fact that the 3 angles must sum to 180 degrees.
okay.
Does that make sense?
Yeah.
So that would let me figure out angle A, but I'm not done yet because I want to find side A.
Description.
Well, to find side A, then what I could do is a step 3, use formula 1 here that I circled and plug in angle A, then solve for side A. Folks, so this one is a little bit of a tricky problem because they really didn't give you in this problem exactly what you needed to use law of cosines immediately, right? Instead, you had to kind of do some extra work and use law of sines to find angle B. Then once you knew angle B, that would let you find angle A. Once you knew angle A, then you had everything you need to use formula 1 to find side A. Does that make sense on this one? Folks, I'm going to let you try this one. Let me know if you have questions. But I wanted to just help you set up this example because it was a little different than some of the others. Okay? All right, folks. Well, I wanted to then go to section 10.3 and introduce this idea of using what are called polar coordinates. So, you know, the idea here with polar coordinates is to kind of give us an alternative way to solve problems. Because sometimes it's easier, instead of working with XY coordinates, to work with something called polar coordinates. Let me give you a quick example of the difference and why this might be useful. So let's say that I'm starting from my house. Let me redo this. Let me draw this better here. Let's say I am starting out from my house, which is located here at the blue dot.
What does it mean to you?
And I want to be able to go from my house to the grocery store. And let's say the grocery store is at this red dot. Okay.
What does it mean to me?
And let's say to get to that grocery store, I have to go 4 miles to the east and then 3 miles north, let's say. Right, so to go from this red blue dot to the red dot, I would go 4 over and 3 up on this map. So in the rectangular coordinate world, I would write that as 4, 3. Right? You've worked with these kind of XY coordinate points in algebra, and we've worked with it here in this course. So this is rectangular. But here's what's new. Let me draw another set of axes all over again. What I'm going to do now is still start at the blue dot. And I still want to get to the grocery store. So I still want to go from this blue dot to the red dot. But instead of going horizontally and vertically like we just did, I'm going to do this differently. Here's what I'm going to say to you. I'm going to say to you, get in your car and assume your car is facing east. I'm going to say drive at an angle of 30 degrees. So drive at an angle of, let's say, 30 degrees. and keep driving for a distance of 5 miles. That will get you directly from the blue dot, your house, to the red dot, the grocery store. So instead of going horizontally and vertically, like we did here, you're really going to go in a straight line distance
I don't know.
from one point to another. You know, and if you think about mapping software, like if you use any kind of apps on your phone, like Google Maps or Waze or any other apps like that, it always tries to give you the straight line distance and the straight line directions. So this idea of giving you an angle and then a distance is called polar coordinates. So this is polar coordinates. It makes a lot of sense in many applications, right? Because many times you want to focus on a straight line distance or a straight line set of instructions to get from point A to point B. So for this polar setup, we need 2 pieces of information. I need to know what angle to point my car at. We're going to call that theta. And I also need to know the distance to go along that angle. We're going to call this r. And then we're going to write this location for this red dot as r comma theta. So in my example, instead of writing 4 comma 3, which was the rectangular coordinates, this was like the XY point, instead, I'm going to write this red dot as 5 comma 30 degrees. And it's really getting me to this exact same location, right? So 4 comma 3 in the rectangular world is really equivalent to 5 comma 30 degrees in the polar coordinate world. So any of these points that we used to plot as XY points, instead we can plot using polar coordinates. And we want to be able to know how to switch back and forth. So if you have rectangular coordinates to start with, how would you translate and rewrite it as polar? Or the other way around. What if you start out with polar coordinates and you want it to go back to rectangular coordinates? So we're going to see there's simple formulas to convert back and forth. All right, so I just wanted to give you that quick overview that we're really going to be working in like a totally different system now. And instead of using XY points, we're going to be using points that are really specified as r comma theta. And, you know, if you want to think of it as a new kind of graph paper, you remember when you were graphing straight lines back in algebra, you used graph paper. Well, to do graphing in the polar world, there's also graph paper, but it's different. It's a special kind of graph paper that I'll show you in a few minutes, and WebAssign will also make use of this special kind of graph paper. All right, so as I mentioned, here's the idea. Instead of writing an XY point, instead we want to write it as an r comma theta point. All right, so if you look at this blue dot here, I could write it as x comma y. But an alternate way to write it is r comma theta. What that tells me is rotate this angle theta and then walk out on this blue line a distance of r, and that'll get you to that blue dot. Now we always write it in the order r comma theta. You know, just like you write rectangular points always in XY, you always put the X number first and the Y number second. In the rectangular world, we always write this r distance first and the angle theta second, always in that order. Okay, so let me give you a quick example. Let me come here. How about if I wanted to plot this point? Here's the point. It's 2 comma pi over 4. All right. Let me write this in degrees just to make it a little easier. Well, pi over 4 is the same as 45 degrees, so I could write this also as 2 comma 45 degrees. All right, so how am I going to graph this? Well, first I'm going to start off with something called a polar grid. Now, let me explain what this new kind of graph paper looks like. What this new kind of graph paper is going to give you are these radial lines, kind of like these spokes coming out. And these spokes are going to allow you to figure out the angle of the r comma theta point. And then you might notice there's these concentric circles. I don't know if you can see it. Here's one circle. Here's another circle. And these circles are going to be different r values. You can almost think of it as like the radius of the circle. You know, for example, let me draw it in different colors. Maybe that'll be better. This black circle, you can see, has a radius of 1. So this black circle corresponds to r equal 1. This red circle has a radius of 2. So any point on the red circle has r equal to 2. And of course, I'll do one more on the blue circle. This blue circle has a radius of 3. So any point on the blue circle is r equal 3. All right, so what I want to do then is plot this point 2 comma 45 degrees. So first I'm going to rotate 45 degrees, which takes me to this radial line here in blue. So that radial line represents the angle 45 degrees. But I want to go out a distance of 2 along that blue line. So what that means is I walk out until I get to the circle that represents r equal 2. And at that point is point 2 comma 45 degrees. Okay? So again, what we did first is you rotated whatever angle was specified. In this case, it was pi over 4. That was that blue line I drew. Then walk out on the blue line a distance of 2. That was represented by that black circle I drew. And at the intersection of that blue line and the black circle, I plotted the point. Okay, so notice how this is a different kind of graph paper. It has these concentric circles, and it's also going to have these radial lines on the graph paper as well. All right, how about if we do one more example? This one says, plot the point 3 comma pi over 2 on this polar grid, on this polar graph paper. Well, I know pi over 2 is 90 degrees. So this is really asking me to graph 3 comma 90 degrees. All right, step 1 is rotate 90 degrees. So of course, this angle here is 90 degrees. And then walk out a distance of 3. And that's going to put me right here at this black dot. So that's the point 3 comma pi over 2. All right, so it just takes a little bit of getting used to on how to plot these polar points. But again, you're going to rotate according to the angle that's given, and then walk out a distance of r according to the value of r that's given and plot the point at that location. Okay, and you can imagine how many applications might use polar coordinates. You know, think about a autonomous car trying to navigate from point A to point B, right? It'd be much more efficient to think in terms of r comma theta than in terms of x comma y if you're programming software for an autonomous car. The same thing for a space shuttle. You know, if you're doing programming for a space shuttle, and you want to get the space shuttle to a certain point. Let's say you want the space shuttle to get to the International Space Station. It's much more logical to use r comma theta type of analysis as opposed to x comma y, okay? And by the way, folks, if you go and take calculus at some point, this analysis we're talking about here in 2 dimensions can be extended to 3 dimensions. I mean, what we're talking about right now is kind of working on a flat piece of paper. But if I was really programming, the software for the space shuttle, I'd have to be working in 3 dimensions, which we're not going to cover in this course, but later courses, you will work in 3 dimensions. In fact, if you take calculus 3, calculus, the 3rd course in the calculus sequence is based on 3-dimensional type of analysis. All right, folks, let's do some examples from WebAssign. And it says here, plot the polar point. All right, so let me think about this. And so they're giving me the point 3 comma 5 comma 5 pi over 3.
He's going to get the home run. Bam.
Now, maybe I want to change from radians to degrees. It might be a little bit easier to work with. Let me change from radians to degrees here. Quick reminder, if I want to convert from 5 pi over 3 radians into degrees, does anyone remember what do you multiply this by in order to change from radians to degrees? You might remember it was either pi over 180 degrees or it was 180 over pi. Does anyone remember which fraction I should use? Well, the way I remember this is I know I want to cancel out the radians. So that means I need radians on the bottom to cancel out this radian on the top. So that means I should really set this up to be 180 degrees over pi radians. All right, so let me do this conversion. I'm noticing the pi's cancel out. And then this is going to be 5 times 180 divided by 3. And if you work that out, it turns out to be 300 degrees. So this polar coordinate is really 3.5 comma 300 degrees. All right, so let me see which answer choice here makes sense. So remember, I want to rotate 300 degrees. Let me try to do my own diagram here. I'm going to be rotating 300 degrees. That takes me to somewhere about here. This is rotating 300 degrees. And then I'm going to walk out a distance of 3.5 on that radial line. And I'm going to put a dot there. So this black line that I just drew is a distance of 3.5. Well, if you compare my diagram to the 4 choices, you can see there's only one answer that is feasible here. It's got to be this upper right corner diagram. Right, it's the only plot that has a black dot down in the vicinity of 300 degrees. Now, you might say, how do you know that that black dot is at exactly 300 degrees? So I guess what I'm saying is this radial line right here is 300 degrees. But how do you know that? Because it's not really marked as 300 degrees. Well, here's what I could do. I know that pi over 2 up here top, this is 90 degrees. And I know, of course, here is 180 degrees. And down on the bottom here, I could label this as 270 degrees. Now you might notice in each one of these quadrants, there's 6 sections or 6 pie slices. Can you see this? Let me try to label this so you can see it here. Here is Let me try to write it a little carefully here. So I'm going to label this as pie slice number 1. Here's pie slice number 2, 3, 4, 5, and 6. Can everyone see these 6 small sectors or 6 small pizza slices? Well, going from slice 1 to slice 6, I've spanned 90 degrees, right? If I add up those 6 pizza slices that I just labeled, it totals 90 degrees. So that must mean each sector or each slice is 90 degrees over 6. So I'm going to say each slice is 90 over 6. But 90 divided by 6 is 15 degrees. So what that means is when you look at this polar graph, each one of these angles is a measurement of 15 degrees. All right, so that's useful when we're working with this graph paper to know that each one of these slices measures an angle of 15 degrees. Well, now I can figure out our 300 degrees precisely. Because notice here is one slice and here is a second slice. But each one of those slices is 15 degrees. So slice 1 plus slice 2 is 30 degrees. 30 plus 270 means this angle does have to be 300 degrees. All right, so when you do some of these WebAssign examples, it's going to be helpful to know that each slice is 15 degrees. And then each concentric circle you could see is labeled as a radius of either 1, 2, 3, 4, or 5, according to the labels there on the horizontal axis. All right, so it takes a little bit of getting used to for this new kind of graph paper, but let's do a couple more examples. All right, so here's a WebAssign example where they're giving you a black dot and they're asking you to figure out the r comma theta coordinates for that black dot. Okay, so the question here is, what is r comma theta for this dot? All right, well, let's figure out the angle to begin with. Well, to get to the radial line, here's the radial line, I'll draw it in red. I would have to rotate this rotation. So how much rotation is that? Well, again, it's hard to know that because the radial lines are not labeled on this graph paper, but I could do a little detective work. I know this rotation is 90 degrees to get to this vertical axis here. So that's 90. And then remember, we said each one of these slices is 15. So here's 15 degrees, and then here's another slice, 15 degrees. So this distance right here is 30 degrees plus 90 means this whole angle must be 120 degrees. So I know theta is 120 degrees. Does that make sense how we figured that out? What we said is to rotate to the vertical axis is 90, but then I've got to keep going 2 more sectors or 2 more slices. And from the previous slide, we said each one of those slices is an angle of 15 degrees. So that's an extra 30 degrees that we rotated. So 90 plus 30 is 120. All right, what about R? Well, R is how far out you walked to get to that black dot. Well, if you notice, I'm walking out until I get to this circle, and this blue circle is a radius of 2. So that must mean r is 2. So the answer to this question is 2 comma 120 degrees. Or if you wanted to enter this in radians, you can convert 120 degrees, and that would be 2 pi over 3 radians. Okay, so remember, WebAssign will take an answer either in radians or degrees. It's just that when you want to enter an answer in degrees, make sure to put the degree symbol as part of your answer. If you leave the degree symbol out, WebAssign assumes you are entering an angle in radians. All right, let me do one more example like this, then we'll move on. All right, here's another question asking you to come up with the polar coordinates for this black dot. Well, this one's a little easier because the black dot happens to fall on this radial line. And that radial line is kind of easy to figure out the angle of rotation because you know that would be 180 degrees. And then I have to figure out r. R is the distance to walk out along that radial line to get to the black dot. But you might notice this black dot is falling on the circle with a radius of 4. So that must mean you walked out a distance of 4. So in terms of r comma theta, I walked out a distance of 4 after rotating 180 degrees. Of course, if I want to enter this in radians, you remember 180 degrees is the same as pi radians. So I can also enter this answer as just 4 comma pi. All right, folks, any questions here on working with polar coordinates, looking at these polar graphs? All right. Folks, let me mention 1 or 2 more items to wrap up today. All right, now, it turns out that in this kind of an analysis, we could have an R that's a negative number. Let me try to explain this. R in some of these examples might be negative. Let me go to the next slide to just show you an example of that. So notice in this example, it says -2 comma pi over 6. So this is -2 comma pi over 6. And I want to be able to graph this point. You might say, well, how can you have an R be a negative number? That doesn't quite make sense if R is like the distance you travel. Well, R is the distance you travel, but it's a directed distance. So R equal -2 means walk in the opposite direction as if R equals 2. You know, if I told you to walk 2 miles east, the opposite of that would be walk 2 miles west. If I told you walk 5 miles north, the opposite of that would be walk 5 miles south. So the way to plot a negative R on a grid is to do it this way. First, plot the positive R. So I'm going to plot 2 comma pi over 6 to begin with. You might remember pi over 6 is 30 degrees. So I'm going to plot 2 comma 30 degrees to start with. Well, here is 30 degrees, and I'm walking out a distance of 2, so here's the black dot for 2 comma pi over 6. But that's not really the point I want. Remember, I want -2 pi over 6. What negative 2 pi over 6 means is reverse the direction. So instead of drawing the blue line like this, have it go the other way and walk out a distance of 2, but in the exact opposite direction. So that takes me to this black dot. So let me say that again. If you want to plot a negative r, first pretend like it was a positive r. Draw that point. Then reverse direction. Instead of going out that direction to, it's almost like turning around and walking in the opposite direction to. Does that make sense how we set that up? Let me go back to the previous slide just to kind of explain what they're doing with this previous slide. What they're trying to show you here is if r is a positive number, then graph normally and plot this red dot here, r comma theta. Because you walked out a distance of r in this direction. But if you wanted to plot negative r comma theta, instead of walking to the upper right, you would turn around and walk in the opposite direction, a distance of r that I'm showing with this blue line. Okay, so here's what they say. If r is negative, then the point you want is on the ray pointing in the opposite direction of the positive r value.
Stop the glass. Later after class. Later after class.
All right, folks, let me mention one last item to kind of wrap up for today. We'd like to know how to convert back and forth from polar to rectangular or rectangular to polar. All right,
Those are the formulas you have to use then.
Today, Sergeant.
Those are the formulas you have to use. It's cosine theta equals x over r, then x equals r cosine theta, then sine theta equals y over r,
yeah,
and y equals r sine theta.
Yep, exactly. Now, Gennaro, right now we're talking about going from polar to rectangular. Okay. And if we're going to go from polar to rectangular, what that really means is you're going to be given an r comma theta point, right? So you're going to be given some r comma theta, and you want to find the corresponding x comma y.
Yep.
To do that, you're really going to be using these formulas that I'm going to circle in red. Let me circle in red. These are really the formulas to focus on. This first formula, it says x equal r cosine theta. That's going to give you the x value you want. The second formula, y equal r sine theta, that's going to give you the y value that you want. So if you want to go from polar to rectangular, use these two formulas that are circled in red here. And you might say, where did those formulas come from? Well, what they were trying to show you is if you draw this little diagram and think about sine theta. Here's angle theta, right? What is sine theta? Well, sine theta is, notice it's a right triangle. So sine theta is opposite over hypotenuse. But when I look at my little diagram here, the opposite side is the red side y, right? And the hypotenuse is the blue side r. So sine theta is y over r. But I really want to solve this equation for y. So let me write it here. I have sine theta equals y over r. Let me cross multiply. I'm going to put the sine theta over 1. Cross multiply. That would give me 1 times y, which is y, and multiplying the other way is r sine theta. So they just wanted to show you where these formulas are coming from. And really, they're just based on the definition of sine and cosine. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. All right, let's do a quick example and we'll wrap up for today. Let me go to an example. Let's do this example. It says, what if you have 3 comma pi over 2 and you want to change it into rectangular? Let me draw a 3 comma pi over 2 just so we get a sense. Well, pi over 2 means rotate 90 degrees. So here's the rotation 90 degrees. And then r, I would walk out a distance of 3. So I'm going to put this blue dot here. So this was r equal 3. All right, well, let's convert it. X is r cosine theta.
What border? What border?
But in our example, r is 3. Theta is pi over 2. Does anyone remember what is cosine pi over 2 from the unit circle?
Okay, go ahead. Yes,
Anyone
sir.
remember cosine pi over 2? Well, if you go back to the unit circle, cosine pi over 2 is 0. So this is going to be 3 times 0, which is 0. Let's do y equals r sine theta. So that's going to be 3 sine pi over 2. I want to remember sine pi over 2 from the unit circle. Well, sine pi over 2 is just 1 from the unit circle. So that's 3 times 1, which is 3. So what it's telling me is the xy point here is 0, 3. Which of course makes sense because if I think about this blue dot, the location of this blue dot in rectangular coordinates, it is 0, 3. So this is kind of an obvious example where converting from 3 comma pi over 2 in radians, in polar, gets me the xy point 0, 3. All right, so we'll do more examples next time. So next class we'll focus on converting back and forth from polar to rectangular coordinates. Again, polar is r comma theta format, and rectangular is x comma y. And we want to be able to convert back and forth between these two kind of coordinate systems. All right, folks, any questions here on polar coordinates so far? All right, we'll finish this up on Monday. Folks, have a good weekend. If you're working in WebAssign and you get stuck, please email me, or the best thing is to actually use the Ask My Teacher button in WebAssign.
Last semester when I used that, like the teacher didn't even get back to me at all.
Well, Gennaro, I am checking that very often.
Yep.
So I will try to get back to you as quickly as possible.
All right.
So please use that.
I already finished 10.2 already.
Good work. Good work.
I'm already on 10.3.
Good. All right, folks. So feel free to log off if you have no questions. Again, thanks for joining. I'm going to stick around for a few minutes. So if anyone has a question on law of sines, law of cosines, polar coordinates, feel free to stick around and ask any questions. If you don't have questions, then I'll see you on Monday. All right, folks, if there's no questions, I will close out. And again, folks, thanks for joining and have a good weekend.